It's really good to see you all coming back from your tea and cakes. So obviously that's an interesting topic for everyone. So let's get started. So we only have 30 minutes and there are all the talks following us. So the topic of today is going to be, wait for it, not AI, but embracing Karpenter to scale and optimize and upgrade Kubernetes clusters. So with all the AI hype, I was told you have to put, or at least mention AI at some point. So that was my contribution today. So without further ado, I know Liz has asked that question initially during her keynote, but can I get a raise of hands? How many of you are like day-to-day involved with Kubernetes and operating clusters? Okay, cool. Decent crowd, like most of you. So obviously the right audience. So if we quickly start, you obviously said you're managing Kubernetes clusters, but you're probably aware that one of the most kind of common issue that you would see on a cluster, or like the one that's the most popular one, is probably the crash loop back off. And obviously, it doesn't tell you much. It can be multiple things that's happening there. There might be other ones that you see, operating clusters as well, such as this one. So you have a bunch of pods, which are just waiting to be scheduled and in the pending state. It can mean many things, obviously. It's not necessarily related to scaling, but by talking about auto-scaling solutions today, I hope you're going to address at least some of that. I mean, obviously, if you kind of dive into that more, you could figure out more details, but what I actually found during my kind of experience working with clusters is errors are not usually very kind of self-explanatory. Even by using AI, you cannot really tell what's happening unless you really kind of dive deep and understand what's happening. And by using something like Karpenter, I hope at least some of you will kind of, I'm not trying to convince you, but I hope you're going to see it's a really good solution to kind of avoid at least some of those issues, right? Right. So maybe first of all, why I'm here, I'm talking about Karpenter. What experience do I have? Like Josh said, I'm Marko. I work as a principal consultant at a company called Scale Factory. We used to be a smaller consultancy company, recently acquired by a larger one called 1010, so we're part of that group. My background is mostly ops, so I come from infrastructure, all the good stuff like we heard in previous sessions, like I used to run Puppet, I used to run Chef, so kind of familiar with that. And kind of throughout my career with the industry, I progress into different roles. My consultancy gig led me through working with different companies across different kind of industries, and I was wearing different hats as part of that. And of course, as part of the journey, I got involved with a lot of like different cluster configurations and kind of cluster errors that people kind of face. I'm also an open source contributor. You can find me in cloud native space. I'm one of the Helm chart maintainers. I also took on the AWS Vault fork, active fork that we're currently maintaining, and I'm also an active supporter and maintainer of some other projects as well. As part of that, I'm HashiCorp Ambassador, probably not the most popular title these days, and also OpenUK Ambassador and Community Builders from AWS. When I'm not doing all of that, I'm fan of automation, simplifying, hiking, and traveling. So yeah, another reason why I'm actually telling you this, you've probably seen that picture like a million times already, but we are actually part of that ecosystem. We're right there, this little small square. So Scale Factory is also one of the certified Kubernetes providers, service Kubernetes providers, yes. I have to read it. So one of the reasons why I'm actually talking about that today as well. Right, so let's kind of switch gears, start from the beginning. If you look at the types of scaling you can do in Kubernetes, obviously there are different types of resources you can scale. You can scale pods, you can scale nodes, and there are other resources that probably are not typical resources to scale, but they're like storage and network that you have to manage as well. Today, I want to focus mostly on scaling nodes, not pods. And there are a couple of types of scaling you can do, both on nodes as well as pods. So you can vertically scale. So if you're vertically scaling, you're literally making resource bigger or smaller, but it means that you're taking the unit of compute and you're just vertically kind of making it bigger or smaller. A different type of scaling is horizontal scaling, where you have a type of compute, and instead of making it bigger and smaller, you're actually adding more of the same. So you can add one, more, or three, or more. So those are kind of basic types of scaling and basically what we're going to address today. Something to keep in mind, I hope you're aware of that, in Kubernetes, even though it has support for scaling, it doesn't come with auto-scaling out of the box. So when you spin up a fresh Kubernetes cluster, it doesn't scale. You can obviously add manually compute, but it won't scale it automatically, and it won't take it away. So something to keep in mind. Right. So if we continue along that line and talk a little bit more about scaling challenges that you can face scaling Kubernetes cluster is, so for example, what you usually face when you don't have an auto-scaling solution in place is something like maybe pending pods with no matching capacity, what we've seen earlier when I showed the error. So you have pods, and there is no capacity that actually those pods could be scheduled on, which could be a problem and might involve some either manual intervention if you don't have auto-scaling, or might take autoscaler to kick things up and make sure that there's enough capacity available. You could kind of hit a situation where you have to over-provision. So there might be different reasons why you want to over-provision, either to avoid the first thing that I mentioned, or, for example, let's say you have spike events when you know there's going to be a huge spike in the load. So you might actually want to over-provision your capacity to make sure that your pods can actually scale up sufficiently quick to kind of fill that demand. Also, another typical scaling issue would be lack of flexibility. So, for example, when you scale, you have to accommodate for different types of workloads. So, for example, if you're mixing different types of compute, classes, or like spot instances, on-demand instances, or like GPUs for AI training, most of the autoscalers wouldn't have that flexibility out of the box. So some of the existing scaling solutions would address some of those things. So, for example, and this is not a take on Cluster Autoscaler, but I'm just using it as an example because it's supposed to be like the most used autoscaler out there. Those solutions tend to kind of try to address some of those issues. So, for example, Cluster Autoscaler would work on the node group level, but unfortunately, because it doesn't work on the pod level, you don't get the flexibility that you might actually want, and actually bin packing that you get with the pods being scheduled on different nodes is suboptimal, so you have some over-provision capacity left. There might be slow reaction times as well, so when you kind of have those kind of quick bursts of scaling events, what Cluster Autoscaler or similar solutions might need long time to kind of ramp up the capacity so your pods get scheduled. And maintaining that might be complex or might take, very intense kind of operational overhead to kind of maintain that and make sure that you're either upgrading it or making sure that you're adopting configurations based on your workloads. So what's the price of efficiency we're paying here, literally? So what I've actually mentioned throughout the problems that were kind of laid out earlier is you end up with operational overhead. So by maintaining the cluster, you're spending more engineering that you probably want to. So unless you're working in Kubernetes development, probably maybe you shouldn't be spending your engineering power in maintaining and making sure that your clusters can scale. It might be really hard to detect and manage drift. So what could happen as well is maybe your configuration comes out of sync with your actually provision capacity. So that might be harder to detect and manage from those autoscalers. And that could lead to, like I mentioned earlier, wasted compute. So you either have over-provisioned compute or, underutilized compute where you cannot actually fit all the pods in, but they still need to be scheduled somewhere, right? And consequently, you kind of end up with higher costs, right? So in order to run this, it would cost you more because the compute is just underutilized. And again, what we do at Scale Factory, we mostly work with SaaS-based companies, and in SaaS work, you would usually end up with multi-tenancy problem as well, which kind of adds additional layer of complexity where you need to accommodate different requirements for different tenants within the same system, and that just makes it so much harder, right? It just kind of exponentially grows in terms of complexity. So the question here is really, what can you do to kind of address all this? And the argument today will be you should definitely consider or at least look at something like Karpenter, which is an open source node lifecycle management solution. It was developed by AWS as part of the AWS Labs, but it was donated to CNCF, I think, a year back, if I'm not mistaken, or something like that. So it is part of CNCF now. And since then, it has actually quite wide adoption throughout the ecosystem. So there is a provider, obviously, for AWS, as well as Azure, IBM Cloud, Alibaba, GCP. There is a start to GCP. There is a reason for that. Even though it has been released a few months back, they haven't had a final, like a release yet, but the code base is in active development. So if you're on GCP, you can expect something to be ready soon-ish. So what is Karpenter, or like what the intent of the Karpenter is, it replaces autoscalers like Cluster Autoscaler with a smarter and faster, or hopefully simpler scaling solution as well. It's kind of driven throughout the usual building blocks of Kubernetes, so you kind of drive it through controllers and CRDs. I'm going to show you examples later. I have a demo ready up. Hopefully the AWS gods will be with me today. We all know what happened yesterday, so what can go wrong, right? One of the biggest advantages of Karpenter would be it provisions nodes directly. So it's actually not bound to any node groups or autoscaling groups in AWS. So when it provisions nodes, it communicates directly with the API backend and provisions exactly the capacity you need to schedule all the unscheduled workloads that you're currently running. And when I say it's an intelligent and high-performance compute management solution, what I mean by that is when it tries to find the compute, it always looks at the cost as well. So it tries to optimize not just for the capacity, but also the minimal cost that would be required to satisfy the capacity that you need, which I think it's probably unique in that space, or at least I'm not aware of a similar solution that would kind of take all those kind of different dimensions in play. Right, we're gonna look at two different, let's say, dimensions or like different things that Karpenter does on a high level. So I'm not gonna kind of dive into very much technical details, but what I want to take you away, what I want you to take away from this talk is Karpenter in a 10-foot view, what it does scheduling, and it does consolidation. If we look at the scheduling first, what does that mean? Again, it works in tandem with the Kubernetes scheduler. It's not tightly bound to Kubernetes. So for example, if you're using something like Cluster Autoscaler, you always have to use Cluster Autoscaler for the version of Kubernetes that you're running it on, whereas Karpenter actually works independently of the Kubernetes version that you're using. It just communicates with the API backend. There are two basic components, so it uses Karpenter Core and Karpenter Provider. Core is the core functionality, whereas the provider is just the cloud provider-specific implementation of the core. Because we work in AWS, my examples will be in AWS, but if you're working with other clouds, the same principles would apply, regardless which cloud you work in. So it works on a node claim basis, so when the capacity is required, it creates a node claim. In AWS, it just communicates with API directly, provisions an EC2 fleet, initiates EC2 fleet API command to just provision nodes directly. And then it just creates the node bindings ahead of time within the control plane. So when the node comes up, it's immediately bootstrapped and ready to go. And as you're going to see later, it works really, really quickly, actually, compared to other solutions. Like I mentioned earlier, it dynamically chooses and launches best suited compute resources, so it supports both scaling up and down as well as in and out. What I mean by that is it's adding capacity and removing capacity, and it can also actually scale down to 0 if required. So if you don't run any of the workloads, it will just kind of take all the compute away. As soon as you want to schedule something, it will just add compute in. When it does all of those things, it's actually use native scheduling constraints. So if you have PDBs defined, so budget constraints or AZ affinity or other things, it's kind of obeying all of the scheduling constraints. So as it's trying to find compute, it's kind of taking all of that into account as well. So the second part is the compute consolidation. If you look at this, so I mentioned when you need new capacity, it will go and provision it, but it also knows how to consolidate existing capacity. So for example, if you have Kubernetes running, pods scheduled, and over time, some of the pods might be scaled down. There might be extra capacity available. What it actually does, it goes about and reschedules the running pods into existing nodes or underutilized nodes and remove the nodes that can be removed. And it's running those kind of simulations constantly within the controller to make sure that it's always kind of keeping up with the demand and compute available. It can also launch new, more cost-efficient nodes as well. So for example, if at some point, let's say your cloud provider changes pricing, you can actually go provision cheaper nodes and reschedule all of your workloads to cheaper nodes and just remove the existing ones. So it's always trying to kind of keep you running in the most optimal way that you can. When it does that, it actually does it always with the least disruption. So like I said, it's always trying to reschedule the fewer available pods. So when it creates disruption to the workloads, it always tries to find the optimal path to kind of cause the least possible disruption for your workloads when you run pods or deployments or anything else. It also is aware of drift detection. So if your configuration drifts, it will always try to consolidate it back. So it will always try to reconcile it to whatever your configuration is. If something happened in the back end, let's say, I'm going to try to demonstrate it later. So for example, you could actually go and change bump the node version in the configuration. It will automatically detect that, oh, your currently running nodes are older than what you have in the configuration. Let's just go and replace all of them, which is quite cool, actually. And there's another really cool thing in terms of compliance. You can actually set the node expiration TTL, and it will always make sure that the nodes never run longer than X amount of time. So let's say you always want to refresh your compute. You can say, recycle all the nodes older than 3 days or like a month. And it will always just recycle those and make sure that they all run smoothly. Right, let's quickly have a look how do you set it up. Like, all sounds great, but like how complicated it is to kind of set it up. Like I mentioned earlier, it consists of core and the provider backend integration. It all comes nicely packaged in the Helm chart. On AWS, you can actually use it as a managed solution using AWS EKS Auto Mode. It's something similar if you're familiar with GCP as GCP Autopilot. I mean, similar-ish. Like, it gets you fairly close, not quite there, but you are not aware that's happening under the hood, or you can manually go and set it up. The process is quite straightforward. How does it look like? First of all, obviously, you have to set up IAM and permissions for the Karpenter to run. Then you go, like I mentioned earlier, go ahead, install the Helm chart for the controllers to run. They're always deployed in high availability nodes, so you always have at least 2 or more of them running. And then you go ahead and apply so-called provisioners, like they changed the naming here. It used to be called provisioners, now they kind of split it apart. As you're going to see later, it's node pool NUS class, where you define what kind of compute you want to choose from. And then just observe and scale, right? It's as simple as that. Oh yeah, it also supports more complex scenarios, such as you can actually run multiple different configurations and put different weights on those and make sure that they're kind of used in, let's say, different tenants or different workloads, for example, right? And yeah, it can actually run in parallel with CA as well. So for example, if you're currently running Cluster Autoscaler, you can actually dedicate a specific part of compute that will use Karpenter, and the rest of it will just run on CA. Let's say you want to kind of test it out and see how it works before you move everything across. And obviously, you can use all your favorite tools for provisioning, such as Terraform, CloudFormation, EKS ETL, like all of that mostly has already implementation or configuration ready for you to use. Right, shall we look at some hands-on code?
Yeah.
Are you sure? Like, yeah. I have more slides if you want more slides. I don't know if it's just the cake or you're just sleepy because of the long day. Okay, how do I get here? Here we go. So first of all, let's have a look what we have here. I'm just going to show you what I'm currently running in my cluster. It's running in AWS. It's completely empty, freshly provisioned. The only thing that I have provisioned is Karpenter controllers, just to kind of save some time on the demo. And then the core DNS just comes with the installation. So what we're going to do next is I'm just going to quickly deploy the provisioner part. So that's going to be a node pool and node class. As this deploys, it's just a couple of CRDs. I'm going to show you in a bit how they look like. So as this applies, I'm just going to quickly scroll up just to show you what has been applied. So what is interesting here is what you can actually do is, so as I said, you have a node pool. And then within the node pool, you can actually define or specify, how the nodes are going to be replaced. So what I'm defining here is a node budget, disruption budget, and I said that I always want to disrupt 20% of my compute at the same time. So for example, if I would go and replace all of the nodes, it wouldn't replace all of them at once. It would go like 20%, 20%, 20%, and so on. Next thing I will define, I can say when I want to consolidate it, I'm going to say only consolidate when empty or underutilized. So you can define that policy as well. Or you can actually say you only consolidate when they're empty. So you can actually fine tune it as much as you can. I can actually specify what my limits are. So my maximum CPUs will be 1,000, and I'm going to use 1,000 gigabytes of memory. Irrelevant for our test, but just to show you that you can actually go that granular as well. And what's actually quite interesting here as well is on the node class, you can actually define so-called requirements. So for example, I only want to choose from the instance types or classes C, M, and T. So I'm only going to pick those types of instances. And I'm going to say only pick instances with less than 33 CPUs. So I don't want to get really expensive ones, right? Because, yeah, that would make somebody unhappy in our finance department. And then again, I'm limiting it even further, so I can actually, I'm actually picking specific types of instances for those classes. I'm actually limiting the availability zones I want to pick from, just to demonstrate that, for example, we won't be seeing any of the nodes from the availability zone B, and I'm allowing both of the architectures here as well. And then for the node class, I'm just defining which AMI types I'm picking, which tags I'm applying to, and some other bits in terms of like which security groups and everything is going to be applied to it. So as we have this ready, I'm just going to deploy an example deployment. It's called inflate. It's literally just a sleep container. It's not going to do anything, just burn through my CPU to demonstrate that I have pods that needs to be scheduled. Before I start doing that, just quickly on the right, what I have here is it's showing us the state of our nodes in our cluster. Currently, I don't have 0 nodes. I have 4 pods. They have been scheduled, but they have been scheduled on Fargate, just so I don't have to provision extra compute for my Karpenter stuff and core DNS. So if I quickly go and say, okay, I want to, let's say, run 10 replicas of my deployment. What should happen immediately, you're going to see immediately said there are 10 pods pending for scheduling. I didn't have any compute, so Karpenter actually figured that out. It's like, okay, there is 0 compute, and it automatically calculated that the best fit for my compute would be instance type C5 for X large, which costs X amount of dollars on demand, which I kind of pre-selected, and it's just spinning that up right now for me automatically. And it happened like you see it instantaneously, literally. It was a couple of seconds, spinning up the instance. As you're going to see, it's going to take half a minute-ish to get the node fully up and ready, bootstrap, included in the cluster. And as you can see, the pods already scheduled. So I already kind of scheduled the pods. They're there. If we check the cluster, you're going to see quickly the pods are there, running, all sorted. Now let's crank it up a bit. Let's say I want 100 pods, for example. Like I just want to say I have initial need for more of those. You're going to see it schedules some of those, but it didn't quite fit in. The rest of it is ended up in pending state. And it immediately kind of calculated we need 3 nodes based on my requirements that would actually satisfy the requirement to schedule those pods. Kind of spun this up, and they're currently spinning up. It's going to take, again, around half a minute. It's literally the time that's needed for EC2 to get spun up and bootstrap and included in cluster. Like this is kind of where we are. And as you can see, one of them is probably ready, and there's going to be soon pods being scheduled on. Here we go. One is done. Second one, third one. Here we go. So if I check my pods, you're going to see we have all of them, or most of them already ready. So what I can actually do here is I want to show you what I said earlier. So let's say I want to upgrade things. So if I show you the nodes, just kind of listed nodes, what you're going to notice is my cluster is 1.34, but my nodes are actually 1.31. You have to trust me on this because it's kind of cutting the line here. So if I want to upgrade this, what I can actually do is I'm just going to change that in the manifest, and I say, fine, okay, we're actually ready to bump to 1.32. Just save it, apply it, and what you're going to see in a second is Karpenter is going to figure out like, oh, my configuration changed. I actually want different types of nodes, and the ones that you currently have actually don't satisfy that requirement. So that what it actually does is it actually went ahead. It's going to start provisioning new nodes and shuffling the workloads across. As I mentioned earlier, it's actually going to do in 20% increments, so it's not going to do it all at once. So as you can see, it spun up a couple of nodes, and as soon as those are ready, it's going to start rescheduling pods of those nodes and immediately just migrating our workloads across, at the same time obeying all the PDBs and all the other constraints that you might have. Before I jump back to slides, because I am slightly time pressured, just wanted to show you something else. While this is doing, I just want to do something else. So you're going to notice none of those, all of those are in A and B, so A and C, no BAZ, AZ, like I mentioned. But I want to just show you something else. Is it does support interruptions as well. So what I can do is I can go ahead and delete one node. I can just say delete node. It's probably going to break it because it's doing other things, but let's go ahead. So I can go and delete the node. So the node gets deleted. And what it actually figures out is like, oh, the node is gone. It has a finalizer on it. It spins up replacement compute immediately. As you can see, it just kind of, because there's a finalizer, it's kind of removed all the scheduled pods. It's kind of provisioning a new node, and it's just going to schedule it there. So this is going to take a while. I just wanted to demonstrate that this is actually working as well. Just going to quickly flip back to this. So just to quickly wrap it up, in terms of what I want you to take away from this session is by using Karpenter, you're definitely kind of leaning more into intelligent scaling in terms of like it supports automated fast provisioning. There is a flexibility and compliance you can actually hit by just using the configuration. And by doing all of that, you can actually massively reduce the overhead. What we've seen working with different customers is not just massively reducing the operational overhead, but also we've seen customers cutting costs down by like 30% or even more. It really depends what kind of workloads you're running. So you might not hit 30%, but in some specific scenarios, it is very beneficial for your costs as well as the operational overhead people spend managing and pathing your clusters. Second of all, it kind of ticks most of the boxes. It supports all different kind of scaling types, in and out, up and down. Like I said, it can scale down to 0. It's doing just-in-time scheduling as well. Like I showed you earlier, it supports availability and interruptions. So, for example, if there is a spot interruption, or if I go and just delete a node, it detects that. It kind of gradually removes the workloads and provisions a fresh node. And you can actually use it as a cost control as well. Something to keep in mind, if that kind of convinced you to kind of maybe have a look at it, there are still some rough edges. We have seen specific scenarios where you run a huge amount of nodes. The calculation can take up a significant time of CPU cycles to calculate. So if you're running more than 1,000 nodes, you might hit an issue. But if you're not at that scale, I think you're pretty safe. Specifically, if you're kind of spinning up large pod images, just keep in mind that it might take a long time to kind of download the image before it kind of spins it up. But there are other kind of approaches you can take to optimize that, either to reduce the size of the image or maybe cache the image as well. And yeah, have a look. There is a Karpenter project on GitHub under the Kubernetes 6. There are plenty of issues open. I would suggest have a look at those, as some of those are issues that might hit you. And yeah, keep in mind that boring is powerful. Focus on the competitive edge that you have rather than scaling solutions. Thank you.